This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Thank you for joining us for the Satellite Book Club seminar series. This is session number 68. Happy fall. Today's presentation, ProbSevere LightningCast from Dr. Michael Pavolonis, a physical scientist from the Advanced Satellite Products branch of NESDIS STAR in Madison, Wisconsin. Our facilitator for the discussion is Sean Campbell, meteorologist from the Washington Air Route Traffic Control Center, CWSU-ZDC. Just a few reminders before we get started that this session is being recorded. There will be an opportunity for Q&A after the presentation. We particularly encourage attendees from our field offices and regional headquarters to weigh in, including any discussion points. Please post your questions in the chat room and we will field them through there. If you'd like to offer a comment directly through your microphone, also indicate that in the chat and we can certainly pass to you. We're always looking for future presenters, so if you have an application that you'd like to share with field offices of the Weather Service, please get in touch with us. And if you're looking for training materials, Brian Mata, the Office of the Chief Learning Officer, can help you with that. I'd like to thank our Tower S team, particularly Kashad Bowman, Lee Byerly, and the Office of the Chief Learning Officer, the GOES-R and the JPSS programs for their support of the Satellite Book Club. Without further ado, I'd like to introduce Mike, who's, as I mentioned, a physical scientist at NESDIS STAR. He leads a science team focused on utilizing artificial intelligence and other techniques to transform large volumes of environmental data into actionable information. Product systems developed by his team include the ProbSevere model, the Fog and Low Stratus product suite, and VOLCAT. Dr. Pavolonis also serves as the NESDIS lead for wildfire product planning, coordination, and user engagement. Mike, welcome back to the Satellite Book Club.
Thank you, Jordan. It's great to be back, and thank you, Kashad, for getting this all set up, and the entire team. And thank you, Sean, for facilitating. So, yeah, what I'm going to talk about today is sort of a newish component of the ProbSevere portfolio called LightningCast. But before I do that, I want to recognize John Centennial of UW-Sims. This is really his work, and I'm honored to represent it here in this forum. But also I'd like to acknowledge the GOES-R program for their support, in particular GOES-R Science. Okay. So, the ProbSevere portfolio, it's actually evolved into 5 what are essentially independent convective nowcasting models. So I think a lot of folks in the field will be familiar with what we now call ProbSevere version 2. It's operational in the National Weather Service. It replaced ProbSevere version 1, which is now retired. That's the original ProbSevere model that predicts the probability of severe, whether severe hail, severe wind, or tornado. And it's available in your AWIPS operationally. But beyond that, there are 4 others. We have a intense convection nowcasting model that is a computer vision approach for identifying patterns in satellite data that are consistent with really intense convection, such as overshooting tops, above anvil plumes. Again, trying to sort of automate image interpretation. We have now what we're calling ProbSevere version 3, which is designed to be an improvement to ProbSevere version 2, doing the same types of things, but trying to do them better. That was first rolled out this year at the Hazardous Weather Test Bed, and I think we had a successful rollout of that, and have gotten some great forecaster feedback on that we'll be incorporating. And then the next 2, these 2 models, more so than the other 3, really address the pre-initiation component of the problem, whether it's pre-lightning initiation or pre-convective initiation. They're relevant to other parts of the convective life cycle as well, but unlike the original ProbSeveres and the intense convection nowcasting, these are really geared towards that earlier stage of development. And so the lightning nowcasting is nowcasting the presence of lightning relative to lightning observations. The convective initiation nowcasting, which is being worked on by a graduate student, Stephanie Bradshaw, is more geared towards predicting when a certain radar reflectivity signal is going to be present. The one I'm going to talk about today is the lightning nowcasting component, which we're calling ProbSevere LightningCast. Okay, so the first thing is, what is ProbSevere LightningCast? So just to try to connect the dots here. So the GLM obviously provides unique observations of lightning. And we know that human interpretation of ABI imagery has been shown to be important for nowcasting lightning, especially lightning initiation. So if you look at the Elsheimer and Gravel paper, we now know this is a technique that's used in a lot of WFOs when they're doing IDSS to determine where lightning may occur in the future, where lightning initiation may occur. So in short, what we've done is we've used a portion of the historical ABI and GLM data records to train a machine learning algorithm to automatically analyze the multispectral ABI imagery, similar to the way a human does, with the goal of nowcasting lightning as observed by the GLM. So, more specifically, LightningCast is an ABI-based machine learning model that predicts where the GLM will observe lightning up to 60 minutes in the future. And it's the gridded GLM data, the GLM products that are on the ABI grid. Okay, so they'll have the same parallax as the ABI. Okay, so how does this work? So as I said, it's a machine learning technique, and the machine learning is from the same family of computer vision machine learning that's used in self-driving cars. So it's really trying to automate image interpretation. It's computer vision. Can the machine or the computer interpret an image in a way that is consistent with how a human might do that? So what it does is it learns the relationship between ABI image patterns in both spatial and spectral space, and the location relative to the location of where GLM observes any lightning in the 60 minutes that follow the ABI image time. And it learns this by feeding it, I think we fed it 76,000 plus images, which when you add up all the pixels is billions upon billions of pixels. So unlike ProbSevere version 2 and version 3, there is no explicit storm detection or tracking. It's a pure computer vision approach that mimics how humans interpret imagery. So the input is the band 2, or the visible reflectance at half-kilometer resolution, the 1.6 micron reflectance, the 10.3 micron brightness temperature, and the 12.3 micron brightness temperature. And so essentially those first three components are the daytime cloud phase RGB. And then in addition, we have this another IR channel here. And these are all provided at half-kilometer resolution. So only the visible data natively is at half-kilometer resolution, but all of the other channels are oversampled to that resolution to make sure that we are taking full advantage of the viz at its full spatial resolution. This does work day and night, so the contribution from the reflective bands 2 and 5, just naturally and gradually ramps down to 0 as you go from day to night. And the model will continue to function with just the IR input. The output is a half-kilometer map of probabilities that GLM will observe lightning in the next 60 minutes. Again, this is relative to the half-kilometer ABI grid because we're using the gridded GLM products. And then we take that half-kilometer grid of probabilities and we do some subsampling and smoothing, and we turn it into contours of probability that are overlaid or can be overlaid on whatever your favorite type of ABI image is. In this case, we're using the daytime cloud phase because that's a really popular one for this type of problem. But you can see the contour overlays here. The ones that we tend to overlay are the 10% contour in dark blue, the 25% in cyan, the 50% in green, and the 75% in magenta. So when I show subsequent examples, you're going to see it displayed just like this with the contours over the top. So just sort of calibrate what those colors mean. As I said, the contribution of reflective bands just naturally ramps down to 0. So this does work day and night. It's applicable to any ABI scan domain. So we apply it to the mesos, the CONUS, or the full disk. And it's applicable to both GOES-East and GOES-West. So GOES-16 and GOES-17 currently. So why did we develop this? There has to be a reason for doing product development. So years ago, the Ocean Prediction Center asked us for a convective nowcasting tool for the offshore region, something similar to what ProbSevere version 2 does. But they, obviously we couldn't rely on radar when we're talking about the offshore and oceanic zones. So given the very limited number of severe weather reports over the ocean, we decided to nowcast lightning because, when you don't have other types of observations, lightning is a reasonable proxy for convective vigor. But while working the offshore problem, it became clear that lightning nowcasting was important for other applications, not just for the OPC applications. So things like impact-based decision support services for outdoor events, airport and air traffic operations, wildfire incident response, and just personal decision-making. So I've actually, I routinely use the lightning, the ProbSevere LightningCast model to make decisions. I'm a meteorologist, so I'm not just somebody in the general public. I know something about the weather, but it's not always easy to judge, when it's safe to be outside in a potential lightning situation, particularly before lightning has initiated. So you can't just look at your radar scope pro and see a line of storms coming at you with lightning. You have to make a decision whether or not, it's safe to be outside, away from being able to take quick shelter. Also, on the back edge of storms, it's a challenge to determine when it's actually safe. So having a tool to help you make those decisions, I found to be useful, whether I'm on the golf course or deciding whether or not to let my kid go on a bike ride at a certain time. The other thing I'll say is that the 0 to 60 minute GLM nowcast is just a baseline capability. It was the first thing we decided to do because we thought it had a really high probability of success while being useful. There are many other models along these lines that are possible. We can do different time intervals. We can do different lightning frequency thresholds. We can even do it relative to ground-based sensors. But now that we've established a successful baseline, as I'll show, we can start thinking about these other things, but we want user feedback before we do that. So here's some examples and some validation to just show you that this thing is working as intended. So I'm going to play an animation here, and you'll see the probability of lightning contours in the next 60 minutes show up. This is the daytime cloud phase. And then you'll also see the actual GLM observations that are time matched with the ABI show up when lightning actually shows up. And that'll be in these relative to this color bar on the bottom left. So I'll just click ahead and get this playing. So this is just in the Midwest in Iowa. So you can see how I'll play it one more time. You can see how the probabilities ramp up ahead of the GLM lightning appearing in this broken line of storms that forms. And so it's, looking at the movie, it's kind of hard to digest all that. So I'll point a few things out. So if we look at a couple different areas of this sort of broken line segment, and we look at the lead time prior to the first GLM flash, and the lead time is relative to what probability threshold you want to use. You use a smaller probability, you get more lead time. You use a larger probability, you get less lead time. So if you were to use the 75% probability threshold in this particular area, you get about 30 minutes of lead time, whereas you get about 70 minutes if you use the 25% probability. You go to another part of the line, you would get 15 minutes of lead time relative to the 75% probability and 30 relative to the 25%. You go to yet another, you would get, again, similar story, 15 minutes with the 75%, 25 minutes with the 25%, and then finally up here, you would get 5 minutes with the 75% threshold and 25 minutes with the 25%. So you can see that the amount of lead time you get is a function of how quickly the convection is developing. Obviously, convection that develops more rapidly, you're going to have less lead time. Convection that develops more gradually, you'll get more lead time. And also, whatever your probability threshold is will determine your lead time. Here's an example of just this applied to mesoscale data. So this is GOES-16 mesoscale sector, so 1 minute data. This is over Iowa again, but this is, a messy scene. There's a lot of high cloud, a lot of mid cloud. There's hardly anything clean about it. The nice thing about the model is it's learned all of these complex backgrounds and scenes. It doesn't need to be a clean field of cumulus in order to work. It can be a messy, complicated scene, and it still provides actionable guidance. And at the 1 minute intervals, it's nice because you get a little bit of extra lead time just with the more frequent observations of the convection. This is just an example to show how it compares to radar data. So on the left is just the probability contours overlaid on a visible infrared sandwich image, and then the GLM will come in when lightning is actually observed. And then on the right is the composite MRMS reflectivity overlaid on the visible infrared sandwich. And we really should be looking at the reflectivity on like the -10 degree C surface, because that's what's looked at for convective initiation most often. This is the composite, but you get an idea here that the probabilities generally ramp up ahead of a coherent convective initiation radar signal. And this isn't a severe example. I mean, an example where there are plenty of examples where the probability contours ramp up way ahead of a radar reflectivity signal. This is one where it's just a little bit of ahead of it, but gives you an idea here. So I know the combination of radar and satellite is typically used by the forecasters to assess lightning initiation, which makes a lot of sense. But the LightningCast model only depends on the ABI, so you may get a little bit more lead time with that. This is an IDSS example. So this was an example that was brought to our attention by Chad Gravel. This is the Rock the South Music Festival in Coleman, Alabama in August. This is August 13th. There were 2 days in a row actually that were impacted by convection here. And so I'm going to play the movie here on the left, and the red circle there is centered on Coleman, Alabama, where the music festival is, and the circle has a radius of 6 kilometers. So a couple things you can see in this loop. It's a really complex scene. It's a lot of surrounding convection, some convection developing closer to the IDSS site. And you can also see it's later in the day. So we go from daytime to nighttime. So you can see how the model transitions from daytime to nighttime very smoothly, no artifacts. And you can see that the event was overtaken by storms, and there was lightning in the vicinity. And based on the National Weather Service guidance, the event was suspended for several hours. I'll play this one more time, because if you look towards the end of the animation, as sort of the storms are winding down in the vicinity of Coleman, you'll see the probability contours get elongated to the southwest. And that actually captures some sort of back-end stratiform type lightning that is sort of the last hurrah of the lightning in this event. And so the model it picks up on all sorts of different patterns that generate lightning, because we've given it so many images to learn from. On the right is another way to look at this, is a time series. So that's the probability of lightning, the maximum probability of lightning within that 6 kilometer radius centered on Coleman in the red line. And then the lightning bolt signals are actual GLM observations within that 6 kilometer radius. So when the GLM observed lightning within that 6 kilometer radius, there's a lightning bolt signal. And so you can see that the probabilities ramp up fairly well in advance, almost an hour in advance of the first lightning stroke. And then on the back end, the probabilities remain elevated until after that sort of stratiform period of lightning, a very brief stratiform period of lightning comes to an end, and then the probabilities ramp down. So, giving the all clear is also really challenging, and the model has all of that sort of built into it. Just one verification slide. We have a lot of verification on this, but this is for completely independent data. So you can see on the left the critical success index for the probability threshold of 40%. The CSI is nice because it doesn't give you credit for correct negatives. So you really have to, when you have the opportunity to detect a correct positive, you really have to do it in order to get a high CSI score. So what you generally see here, and I'm not showing the map of lightning frequency, but the lower CSI scores are almost exclusively where a GLM infrequently observes lightning. So given that you don't get the opportunity to get credit for correct negatives, where you have very few lightning observations, it's very hard to achieve a higher CSI score. But in areas where the GLM more routinely observes lightning, you can see the CSIs above 0.5 are really, really common. Out in the Northwest, these are probably influenced by detection efficiency challenges with the GLM. We know the detection efficiency as you get to larger viewing angles is a bit challenging. And then on the right is the seasonal performance. So the critical success index, we broke it out by day and night. You can see you get comparable skill day and night. And the skill across seasons maintains relatively steady. In the seasons where you have less lightning, again, the CSI is lower, but that's sort of expected given.
Oh, I lost my internet.
Okay, so ProbSevere LightningCast, it is available. There's a link here, and maybe John Centennial will add the link.
Oh, that sucks.
So sorry, does somebody have a question? Okay. So maybe John will add the link to this in the chat. So this is just a screen capture of the web mapping service is one way to display this data. And we have it available for both the CONUS and mesoscale sectors, so both GOES 16 and 17. The model is incredibly efficient. So the CONUS results are available roughly 30 seconds after the end of scan, and the meso results are available roughly 30 seconds after the end of the scan. We also have a link where you can get GR level place files, and those place files have parallax correction in them so that they're ready to be overlaid on radar data, which is what GR is used for. So that's another way to get these. There's also a rudimentary time series capability. So if you right click on any location on the map and you click on probe, you can get a time series probability for that location. If you're on a map, you might want to try the left click if the right click doesn't work. Okay, so the summary, wrap up here. So we think this is pretty unique quantitative exploitation of GOES-R data, where you get a typical lead time is about 30 minutes relative to the first occurrence of GLM lightning, but it's also helpful in determining when lightning is no longer a threat. I will say this, and I say this every talk, AI tools are not a replacement for human expert analysis, but they are really important for enabling consistent, efficient, and timely decision making. One thing that is absolutely uniquely human is communication. Machines can never do that. Machines can help you with data analysis, and it's important that we utilize that given the data volumes, but communication is uniquely human. So making sure that humans have enough time to do that communication will require some help from algorithms and tools like this. User evaluations, and we have several sort of discussions going on with OPC, TAFB, WFOs, CWSUs, AWC. That's really going to dictate the future development of the model, including user interfaces and dissemination mechanisms. We have a baseline now. We have something that is deployed that users can look at. Now we can get users involved in the development because they have something to look at. The existing, in regards to AWIPS, we are thinking about how this will be displayed in AWIPS. The existing ProbSevere version 2 plugin can be used to display the LightningCast contours, but only if the version 2 ingest is disabled, which is obviously no good. Although that works for OPC and TAFB, because ProbSevere version 2 isn't really applicable to their mission. We're seeking, resolution and alternatives for this, and if anybody has any ideas, we'd love to hear them. And then finally, because this model is so efficient, it runs on CPUs in a matter of seconds. One possible concept of operation, should it make it that far, is to deploy LightningCast software on AWIPS boxes so we don't have to worry about bandwidth and pushing more data around. Just an idea, and that's one of the things that machine learning will be really good for. Because it's incredibly efficient to run these models. It's expensive to train them, but it's really cheap to run them. If you're interested in more information, there was a NESDIS news story on this a month or two back. And with that, I will end. And we have time for Q&A. Thank you.
Well, thanks for that great discussion, Mike. Thanks for the great briefing. As a reminder to everyone, please stay on for the discussion, and we do encourage participation from field forecast offices and regional headquarters. And also, please stay on to complete the feedback survey posted in the chat room. In a week from today, on Thursday, September 30th at 12 p.m. Eastern Time, Dr. Curtis Seaman, research scientist from CIRA, will discuss the value of VIIRS. Please contact the Tower S team, Lee Byerly and Kashad Bowman, for questions about the SPC or for configuration of satellite products. More information will follow in an email from the Tower S team. All right, now getting into a few questions here. I believe the first question was from Stephen Rowley. He asks, in the IDSS specific location example, how does the model account for parallax errors?
Right, so it is providing, it's essentially predicting what the GLM gridded products where they'll have lightning. So the forecaster has to make that parallax adjustment. We do have a version of the contours that are parallax corrected, and those are available in GR. So, you know, we have two options. We can provide the parallax corrected contours that will be that perhaps more desired, or we can provide the non-parallax corrected that will have a natural overlay on the ABI. So both options are available. If you want the parallax corrected, GR analyst is the way to go.
All right, thanks for that, Mike. The next question is from, looks like Paul Iniguez, if I have the name pronounced correctly. Is lat long, time of day, time of year part of the inputs?
No, it is not. You know, we've thought about things like that and done some experimenting, but yeah, we haven't seen it have a big impact. So at this point, you know, the goal was just to train this with as many images as we possibly could with the CPU power that we have. And that seems to be sufficient for the model to learn all it needs to learn about different locations and different times of year. Our training data encompass the entire annual cycle and large geographic regions. So that was the approach to handle that.
Okay, thanks. The next question is from Eric Bolt. Are there any GOES-17 verification studies or comments about shallow convection, pulse storms, and other limitations in the West?
We have done GOES-17 verification similar to what I showed for GOES-16. They're in the backup of the slides. But yeah, we have, so the out west, the model verifies much better relative to the GOES-17 GLM than the GOES-16 GLM because of the detection efficiency issues with the GOES-16 GLM at larger viewing angles. So for the Intermountain West and the West Coast, where you do get some shallower convection, the model does tend to verify quite well. In regions where lightning is rarely observed, you'll have lower critical success index scores simply because there's so few opportunities to get a correct detection. But in regions, you know, the monsoon regions, you know, places where you do see convection time, you know, different times of year or certain times of year, it generally the verification is generally, you know, comparable to what we see in other locations with GOES-16 at smaller viewing angles.
Thanks, Mike. This is a comment, it looks like, from Javier Villegas Bravo, if I've pronounced the name correctly. It says, thanks for your work, Mike and John. At OPC and TAFB, we are working with John to get it into our AWIPs in order to run a test bed to improve our mission over the ocean. We are very excited to have this product.
Yeah, thank you, Javier. And yeah, and should mention, yeah, Javier has done a lot of work to sort of plan out an evaluation here with OPC because they were the original target of this work, and we're really grateful for that.
The next question is from Roger Gass. It's actually a two-part question, it looks like. The first part is, how does this model work with high base convection? And the second part is, are there any case studies on this? You may have touched a little bit on that already.
Yeah, as I said, you know, high base convection, particularly common out west, yeah, seems to work well. We have I had several examples in the backup slides, including one from out west, where you can see how it performs. But I mean, I think the you know, the easiest thing to do, because this was available in real time, so, you know, you can go and look at it any single time. I mean, I could show you case studies and things like that, but the, you know, the performance in real time where, you know, we can't pick and choose what we're processing is really where I think you get the best insights into how it performs.
Okay, the next question, another question from Pavolonis is, when was your CSI image for?
The CSI image was, I think, everything accumulated over a subset of all 12 months from 2020. So our training data was from 2019. Our validation data was from 2020. It did cover all of it sampled all of the seasons, the CSI image. We could make those images per month as well, per season. We could aggregate it in different ways, and I know John has a bunch of figures that speak to that. But yeah, it's that was our way of summarizing it for this audience, at least.
Okay, thanks, Mike. And then we have a couple of other questions here. One question is, can the LightningCast model be applied to satellites other than GOES-R?
Yes. So the nice thing that it relies on you know, data that is ABI data. There are other sensors just like ABI or very similar to ABI, including Himawari 8 AHI. So you can actually run this model on AHI, and the next, you know, all of these next generation geostationary imagers, you can run this model, and it doesn't matter if there is a GLM there or a lightning sensor or not. So that's the nice part of it.
All right, another question is, are there other forecast problems that this type of machine learning can help with?
Yeah, this type of machine learning, this computer vision approach, you know, it's really powerful. I mean, obviously, if it can teach a car to drive itself, you know, it can tackle a lot of problems. And you know, some of those are, you can predict what radar will look like from satellite. So if you have, you know, radar outage or beam blockage, or you're outside of radar coverage, something like that can be really helpful. So you can probably do it with regards to hydrological applications. And Stephanie Bradshaw is sort of working that aspect of the problem for our group. And you know, there's anything that any sort of image interpretation that human experts excel at, this type of machine learning can help support.
Looks like perhaps another question would be, how does the GOES-17 loop heat pipe issue impact the LightningCast model?
Yes, so it does have impacts. It doesn't impact the band 2, the visible band, or band or the 1.6 micron band. Those are unimpacted by the loop heat pipe, but it does impact to large extent the 12.3 micron band that we utilize. So for GOES-17, we have a version of the model that does not rely on the 12.3 micron band. So it's a 3-channel model during the day, and it's a 1-channel model at night. And that seems to mostly mitigate the impacts of the loop heat pipe, although the recent computer malfunction on GOES-17 that has resulted in some more significant loop heat pipe impacts that will continue to degrade over time are actually impacting the 10.3 micron channel in ways that are worse than it was before. So that will have some impact. There will be some window of time during the worst periods of loop heat pipe impacts where the predictions may get noisy. But fortunately, you know, GOES-18 is hopefully on the way to address that issue in the next year or so.
Thanks, Mike. We have another 2-part question here. Do you think your methods could be applied to effectively extend your forecast lightning time range to 2 hours or longer? That's the first part. The second part is, what additional training data sets might be needed to extend the LightningCast to 2 hours or more?
Right, yeah, so we only went with an hour, but that doesn't mean that's what we're limited to. the longer you go, obviously, the more challenging it gets. Because right now, the model really cues off of the presence of cumulus clouds and what those cumulus clouds look like in the multispectral imagery. If we were to go to 2 hours, you might start talking about, we don't even have a cumulus field yet. So in that instance, we may have to bring in like numerical weather prediction or some sort of analysis fields that capture environmental parameters. But yeah, I would be confident that you can make a useful model that goes out longer. It may have to rethink some of the components, but yeah, and the longer you go out, the more uncertain you're going to be, obviously. But I think something useful is possible.
Thanks, Mike. This is last chance for anyone else who might have any other questions. I guess I just saw one more here. Let's see here. I think somebody asks, this is a Michael Jamilkowski. I think the question was, is ProbSevere LightningCast only experimental or has it been used operationally? And then there's another couple questions to go along with that. If the latter, what kind of feedback from users have you gotten? And then in either case, what is its verification rate? I think you may have probably touched on the verification rate, and I can speak to the fact that it has been used operationally because I actually have been using it in operations, but you can expand on that a little farther if you'd like.
Thanks, Sean. So it is experimental. This is, not an operation. It's not running in operations. It's running experimentally at the University of Wisconsin. But forecasters have found it. Because we do have a real-time data feed, experimental, and so we do know that there are some forecasters that are looking at it. I don't have a handle on to what extent it's actually used to make decisions, but I know there are some National Weather Service forecaster eyes on it at least, and there's been a good amount of interest in it. The verification rate, yeah, I did touch on that in the presentation. We have like critical success index values that range in places where you frequently see lightning, from about 0.5 to 0.7, which is a pretty good CSI score. But yeah, we have a lot of details on the verification that I didn't go through. But the best thing is, if you're curious, look at the real-time data page or real-time feed and sort of get a feel for it. And I think you'll get a sense for how it does.
Thanks, Mike. I'm going to pass it back to Jordan. It looks like he has a couple of other questions.
Thanks, Mike, for your presentation. Very exciting work here and great extension of ProbSevere methodology. I think one of the issues we have in the Weather Service is lightning at very high latitudes, which, while rare, can pose some challenges for forecasting. So have you looked at the extent of this by zenith angle, specifically up at Alaska and higher latitudes?
We have not gone, we are running GOES-17 CONUS, so that will extend fairly far north, but not well into Alaska. I would say we have looked at larger viewing angles, not necessarily with a focus on high latitudes. But yeah, I mean, the performance seems to hold up okay. The thing that is really challenging is that the GLM detection efficiency does decrease with increasing viewing angle. So that will have an impact on the model, both in terms of its verification and how it was trained and what it was able to learn. But to answer your question, I don't have any. I don't think we collectively have a good idea of how it would do in Alaska at this stage. That would have to be looked at.
And then my other question is, I think your past work might have used some ground-based lightning data. My question is, as far as the probabilities that result when you use cloud-to-ground strikes versus, inner cloud, which is what GLM is seeing, do you notice a change in the probability that's systematic?
Well, the probabilities are only relative to what the GLM will see. So we don't have a version that was trained to ground-based data at this stage. Although that is one of the possibilities that we can go ahead with in the future. But at this point, one of the areas that is understudied, we haven't gotten to yet, is even though this was trained against GLM, how does that relate to what a ground-based sensor is going to see? We don't have an answer to that yet, but yeah, that is a important question and something we'll have to look at.
Okay, thank you. I don't see any other questions coming in. So Sean, unless you had anything else, I will proceed with the wrap up now.
I do not. It's all yours.
Okay, thanks so much, Sean. And thank you so much, Mike, for this presentation. And thanks to everybody who attended today. Very exciting work and something that I think that has the potential to really support our impact-based decision support services and other mission service areas within the National Weather Service. As Mike and Sean have already mentioned, the Satellite Book Club continues every week, including next week, Thursday, September 30th, 12 noon Eastern Time. Curtis Seaman is going to be talking about the value of VIIRS, so going back and talking about polar orbiting data. And so if you're interested in that, which I hope you are, please tune in again at 12 noon Eastern next week, Thursday. Until then, please feel free to contact our Tower S team if you have any questions about the Satellite Book Club or the configuration of satellite products in your AWEPs. We would love to help you with that. Tower S team is always standing by. So with that, as I mentioned at the beginning of the call, hope your fall is off to a good start and you're staying well. We'll see you next week. Take care.